Hey everyone, I'm Mark Stephenson, a PhD student at the AVS lab at the University of Colorado Boulder. And today I'm going to be presenting on optimal target sequencing in the Agile Earth observing satellite scheduling problem using learned dynamics. So first off, what is the Agile Earth observing satellite scheduling problem? We know what a satellite is. An Earth observing satellite is a satellite that's equipped with some instruments used to gather data about ground targets. This data could have heterogeneous rewards. There could be constraints on when these targets are accessible, whether it's due to the relative elevation of the satellite or the time of day, and there could be time-dependent rewards for these targets. In this presentation, we're only going to be discussing heterogeneous rewards and elevation constraints. However, the paper goes into more of these options. Agile is an important term in this problem. Unlike traditional satellites that can only slew side to side for adjusting their imaging field, Agile satellites use all three axes of control to be able to image targets that are both side to side and forward and backwards along track. Finally, it's a scheduling problem. We're looking to maximize the sum of rewards of these image targets. To formalize it, we want to find the times and targets that, in sequence, maximize the sum of rewards. This has a constraint on it, which is that transitions between targets must be feasible. We need to have enough time for a satellite to slew and settle on the next target coming from the previous target. This presents two main challenges for us. The first is that we're dealing with a large combinatorial solution space due to all the possible sequences we could try. And the second is that these transition dynamics are highly nonlinear. So to take a step back, how are we going to model this problem? We use a high-fidelity spacecraft simulation framework called Basilisk that the AVS lab develops. This software has a Python front end and a C++ back end, meaning that it's both easy to work with and has very fast simulation speeds. For this problem, we're modeling everything from flight software, the spacecraft component dynamics such as reaction wheel dynamics, and orbital mechanics, all using Basilisk. We take this to be the ground truth of our system. So to look at how we're going to solve the problem, we go from our Basilisk simulation. We have the goal of finding an optimal target sequence. This reaches the first problem, which is the combinatorial complexity. Simulation is expensive. We can't just try random plans and find a good one. So to solve this, we are going to make an abstraction of the problem where we represent feasible transitions in a graph structure. However, this leads to another challenge. We need to be able to predict what slews are feasible to be able to build this graph. And to do this, we're going to use machine learning to learn the dynamics of what transitions are feasible. Once we have those dynamics learned, we can construct a graph of feasible slews between targets. We can then use a mixed integer linear program solver to solve and find the best sequence. And finally, we can validate these sequences back in our original simulation. So for the first problem of slew transition time, we essentially need to know how long will it take to translate from some initial state with a pointing direction, a body rate, and an orbital trajectory to settled pointing at some ground target. We have a few options. The first is just to use a dynamic simulation. We already have one. We could simulate every potential transition using this controller. This is not a great idea because dynamic simulations are expensive and we have a lot of potential slews that we would need to test. We also could use a simplified model, which is typical in the literature. This would be either a constant or a very low order heuristic estimating what slews are feasible and how long they take. This also has drawbacks. Either it'll result in infeasible solutions if our heuristic is too eager, or we'll lose optimality if our heuristic is too conservative. So instead, we use the approach of a neural network, where we train the network across lots of simulated slews and use that to learn how long the slews will take. This is great because it should work for any deterministic controller, and neural networks are cheap to evaluate, and we need to evaluate many slews for feasibility. So we run the simulation to generate slews, and we regress over them. These slews take up to around 80 seconds, and they aren't actually totally deterministic due to typical things like time discretization, or per axis torque saturation. But by and large, they are relatively deterministic. And we see that our regression is quite good. We're able to estimate 99% of our slews within 4.6 seconds of error. And what that translates to is that for the vast majority of slews, we're under 5% error of the actual slew time. There are some practical considerations for using this network. Since these errors are centered around 0, we still have the issue of heuristics where overprediction is safer but less efficient than underprediction. So we want to add a small margin to these slews. Experimentally, we find that using the 99th percentile error of 4.6 seconds works well. The paper goes into the selection of this margin in a little more depth. Now that we have our slew feasibility or our slew feasibility estimator, we can construct a graph of possible slews. So here on the horizontal axis, we have time. The vertical axis, we have our various requests, and each blue bar represents an open imaging window for that request. We go from our initial dark red state, and we use our slew estimator to estimate how long it will take to slew from that point to any of these targets. We see here that all of these are estimated to be feasible, so we add an edge between the current state and the arrival time from the current state at that new target. We then weight the edge with the value of the outgoing target. So essentially, as we interact with this graph, traveling the edge from the initial vertex to one of the other vertices represents transitioning from that initial state to pointing at the other target. We can then recursively apply this technique. And this is because the parameterization of the slew network was carefully chosen such that you can resolve the inputs to the slew network at any imaging state. So at any combination of a target and a time you're imaging that target, you can then repropagate and test whether it is feasible to transition to other targets from a certain target. We repeat this over and over and construct a fairly large graph. In fact, this graph has a number of edges on order r cubed, r being the number of requests in your environment. Once we have our graph, we can apply a mixed integer formulation. And for anyone who's seen a mixed integer formulation of the traveling salesman problem, this should look familiar. We have our decision variable x, and we want to select to travel the edges that maximize the sum of weights of the edges, so the sum of imaging rewards. This is subject to a constraint that every incoming edge also has to have an outgoing edge. Basically, any target we visit needs to come from somewhere and go to somewhere, but can't come from multiple places or go to multiple places. Finally, we have a constraint of no re-imaging targets. Each target can only be visited once in our sequence. Now, this is coming from a large graph, so it also creates a large mixed integer program. In this case, again, with order r cubed decision variables. We can improve on our feasibility graph by reducing the size of it. We note that there are a lot of edges that are the composition of other edges. So in this case, instead of going from target A to C directly, there's also a sequence from target A to B to C. And we can assume that because it's possible to transition from target A to B and possible to transition from target B to C, the transition from A to C directly is also feasible, but implicitly present in the graph, so we don't need to represent it explicitly. If we remove all of these redundant edges, we get a much sparser graph. In fact, being reduced from a number of edges on order r cubed to order r squared. We do need to modify our mixed integer solver to be compatible with this new graph structure, because as you could imagine, this graph structure forces some situations where transitioning from one target to another target requires passing through a third target that's already been visited, which would violate our no revisitation constraint. So we add a new binary variable y that represents receiving credit for visiting a target. Our second constraint of incoming and outgoing flow in our sequence is the same, but our final constraint, instead of limiting our sequence to visiting each target once, it simply limits us to only receiving credit for visiting targets that we have visited at least once, but the credit doesn't get duplicated for multiple visitations. And we have the great effect of reducing our number of binary variables, even though we've introduced a new one, from order r cubed to order r squared. So now that we have this pipeline for generating our optimal sequences, we're going to run some experiments. We look at two distributions of targets, a uniform distribution and a city-based distribution. We consider request densities ranging from 100 to 10,000 requests, and planning horizons from 1 orbit to 15 orbits, or about 1 day of planning. For the uniformly distributed targets, we get the results that we would expect to see. As we increase the number of requests in our environment, we achieve higher rewards. However, with longer planning horizons, we achieve lower rewards because in the shorter planning horizons, we're able to take greedier actions, whereas in longer planning horizons, we can't be as myopic and we have to optimize over a longer period. We see that our average request reward, when we have fairly few targets, is around 0.5, which is the mean target value. This is because targets are few and far between, so the planner grabs every target it possibly can, and it doesn't have the opportunity to be picky. However, as we reach larger problems, the planner has more targets to choose between at any given time, and it's able to pick higher quality targets. We see the same results with our city distributed targets, both in terms of the total reward as well as the average value of the targets we visit. And in both cases, we see success when we execute these plans in our simulation. In the uniform results, we see that 99.9% of the slews that we attempt in these plans are actually feasible when executed in our basilisk simulation. And with the city distributed results, which are more challenging because of the tight clustering, we see a success rate of 98.7%. And this really indicates that we haven't created a system that is way too conservative, but we also haven't created one that is too eager. Finally, looking at solution times, we see that over smaller instances, so ranging up to about 1,000 targets in the city distribution cases and 5,000 targets in the uniform distribution cases, we're on the order of tens to hundreds of seconds to solve the entire pipeline, with even being sub 1 second for very small instances. A majority of this time is spent by the MIP solver in larger cases, and this really becomes the limiting factor as we look at very dense target environments, such as 10,000 targets over a 15 orbit horizon. In these cases, the MIP solver is limited to 1,000 seconds of planning time, and it terminates with some possible optimality gap. But even in these cases, the optimality gap is not terrible. We see up to a 20% optimality gap, which is an upper bound on how suboptimal the solution is. So in conclusion, we have demonstrated a way of finding pseudo-optimal solutions to the AEOS target sequencing problem, and it's optimal up to a time discretization and graph construction, which I show in the paper is less than a 5% loss of optimality for our 10-second time discretization. It's up to a slew estimator quality, which we saw in this presentation is fairly good, and it is negligible if it is less than the time discretization. And it's also optimal up to our MIP optimality gap, which is selectable depending on how much time you have to let your MIP solver run. And these results are comparable, if not better, both in terms of speed and quality to other solvers such as iterative local search-based solvers. And I think things that are really worth highlighting in this work is that we demonstrate how well it transfers to very large instances of the problem. And we also demonstrate that these solutions can be deployed in a realistic simulation environment to great success. Also in the paper, we have some additional experiments about the slew estimation, as well as shown a modification of the formulation that allows for time-dependent reward formulation. So if you were interested in what was presented here, you should check out the paper. I'd like to thank the AFRL for funding this work, and here are some selected references that were used with the creation of this work. Thank you for listening.